Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you want to find the next Earth, like a literal second home for humanity out there in the galaxy, the absolute worst place you could look is right around a star that looks exactly like our sun.
I mean, which sounds completely backward, right? Because for decades, that was the whole strategy.
Right. You assume you want a carbon copy of our solar system.
Yeah.
A nice, stable yellow sun and a rocky little planet just sitting at the exact right distance.
Exactly. But the data has completely forced us to basically tear up that playbook. Finding a twin of Earth around a twin of the sun is just, well, with our current tech, it's practically impossible.
Which is so frustrating. But that's why today we're talking about venturing into, I guess you could call it the cosmic graveyard.
Yeah, that's a good way to put it.
We're looking at these things called failed stars. And we're getting into all this because of a Canadian space mission called POO-8, which is launching in 2029.
Right, and POO-8 is totally abandoning the blinding light of those bright yellow suns. It is a highly optimized, really aggressive strategy to search in the shadows, basically.
Okay, so let's lay out the scoreboard first. Yeah. Because the numbers here, they really tell a super frustrating story for astronomers.
Oh, absolutely.
Right now, humanity has confirmed nearly 6,300 exoplanets.
Which is just a staggering number to even think about.
It's massive. Just pause and think about that. Over 6,000 alien worlds orbiting other stars that we know exist for sure. But out of that huge catalog, only 223 are actually designated as terrestrial.
Right, meaning they're rocky planets with a solid surface, like Earth or Mars.
Yeah, just 223. So you look at a ratio like that, and it's like, what, roughly 3%?
Roughly, yeah.
It's so easy to jump to the conclusion that rocky planets are just this super rare anomaly in the universe.
But that is a total trap. You really can't look at it that way.
Really? Why not?
Because the vast majority of those 6,000 worlds are gas giants. Or ice giants. They're these massive bloated planets that don't even have a solid surface.
Right, so we're talking about places like Jupiter or Neptune.
Exactly. Environments where the atmospheric pressure is so intense, it would literally crush anything long before it ever reached some hypothetical core.
So the fact that we have thousands of gas giants and barely any rocky ones.
It tells us practically nothing about what's actually out there in the universe. But it tells us absolutely everything about the limitations of our own telescopes.
Okay, so it's classic selection bias.
100%.
It's like if you drag a huge fishing net through the ocean, but the net has these massive holes in it.
Right, right.
You pull it up and you're like, wow, the ocean only contains giant tuna. But really, all the small fish just slipped right through the gaps.
That's a perfect analogy. The tools we rely on are heavily biased toward finding the loudest, biggest things in the room.
Okay, so unpack that for us. Why are our tools so biased?
Well, it comes down to the physics of exoplanet detection. Planets don't emit their own light, right? At least not in the visible spectrum. They only reflect the light of their host star.
Right, they're just bouncing light back at us.
Yeah, so direct imaging, like actually pointing a telescope and taking a photograph of a planet, is unbelievably difficult. It's like trying to photograph a firefly buzzing right next to a lighthouse.
From like 50 miles away?
Exactly. The glare from the lighthouse, the star just completely washes out the tiny speck of light from the planet.
So if we can't just take a picture of them, how are we finding thousands of them?
We have to rely on indirect methods. We observe the effect that the planet has on its star. Historically, we leaned really heavily on something called the radial velocity method.
A radial velocity. Okay, what is that in plain English?
It's basically measuring a microscopic wobble. As a planet orbits a star, its gravity actually tugs on the star a little bit. It makes the star wobble back and forth in space.
Oh, wow. So the star is actually moving.
Just a tiny bit, yeah. And obviously a massive, bulky gas giant like Jupiter is going to yank on that star a lot harder than a tiny speck of rock like Earth would.
So the wobble is bigger.
The wobble is much bigger. The Doppler shift in the starlight is way more pronounced. And our telescopes can catch that signal pretty easily.
Okay, that makes total sense. Big planet equals big wobble equals easy to spot.
Mm-hmm.
But what about the other method, The one that really blew the doors open.
You're talking about the transit method.
Yeah, the transit method, because that's what the Kepler mission used, right?
Exactly. Kepler changed everything. And the transit method is conceptually super simple. It's just an eclipse.
So a planet just passes in front of the star.
Right. It passes directly between our telescope and the host star, and it blocks a tiny, tiny fraction of the starlight.
Okay, but let's run the numbers on that, because I feel like people underestimate how hard this is.
Yeah.
If we take an Earth-Sun analog,
Okay, let's do it.
let's say there's an alien astronomer hundreds of light years away, staring at our sun and hoping to catch the Earth transiting.
Right.
How much light does the Earth actually block?
About 0.01%.
1/100th of 1%.
Exactly. 1/100th of 1% of the sun's total light. And here's the kicker. That dip only happens once a year.
Because our orbit takes a year.
Right. And the transit itself only lasts for a few hours.
That is insane. It's literally like trying to detect a single moth flying in front of a stadium spotlight from miles and miles away.
Yes.
And you're doing it purely by measuring the drop in the spotlight's overall glare.
Which is incredibly hard. And to make it worse, you can't just spot it once. To actually confirm an orbit, you need to see multiple transits.
So you're waiting years and years just to verify a signal.
Years. And you're looking for a signal that is barely distinguishable from background static.
The static. Let's talk about the static, because the stars themselves are not making this easy for us.
Not at all. Stars are not uniform, perfectly static light bulbs. They are violently churning spheres of plasma.
Right.
They have massive sunspots that rotate into view. And those sunspots are dark, so they block light and actually mimic a planetary transit.
Oh, so a sunspot can look like a fake planet.
Exactly. Plus, they have solar flares and internal pulsations that cause their brightness to wildly fluctuate all the time.
So you're trying to find a 0.01% dip caused by an Earth-sized planet amidst all this chaotic, boiling stellar noise.
It's an immense challenge, but conversely, if you're looking at a Jupiter-sized planet around a sun-like star, it blocks about 1% of the light.
Which is huge by comparison.
Right. That is a massive, unmistakable signal compared to the noise floor.
Okay, so knowing all of this, the need for a specialized tool becomes super obvious. If the fishing net has holes that are too big, you don't just keep casting it over and over, hoping for a miracle.
No, you build an entirely different net.
Which brings us to the entire driving philosophy behind the POET mission.
Yes, POET.
It stands for Photometric Observations of Exoplanet Transits. Like we said, it's a Canadian microsatellite launching in 2029. And its sole purpose is to find Earth-size and super-Earth exoplanets.
But the brilliant thing is, they aren't trying to achieve this by building some monstrously huge mirror.
Right, because building a bigger camera to stare at the same stadium spotlight doesn't actually solve the fundamental contrast problem, right?
Exactly. The genius of POET is that it changes the spotlight itself.
Okay, explain that. How do you change the spotlight?
Instead of looking at G-type yellow dwarfs like our sun, the mission is targeting what astronomers classify as ultracool dwarfs.
Ultracool dwarfs, okay.
So, going back to your analogy, if you swap out that massive stadium spotlight for a dim little desk lamp.
Oh, I see where this is going.
Right. And that same moth flies in front of the desk lamp, the percentage of light that gets blocked absolutely skyrockets.
Because the background light is so much smaller.
Exactly. The fractional dip in brightness goes from that imperceptible 0.01% to a highly measurable 1% or even more.
That is such a clever hack. So let's really dig into what makes a star an ultracool dwarf. Because targeting the runts of the stellar litter is just a fascinating approach to me.
It's the best strategy we have right now.
So when we look at the stellar classification system, it's essentially a temperature scale, right?
Yeah.
That also correlates with mass and size.
That's right. Our sun is a G-type star. K-type stars are a little bit smaller, they're cooler, and they glow with a slightly orange hue.
Okay. And M-type.
M-type stars are the red dwarfs. They're even smaller and cooler still, but then you get to the bottom of the barrel, the brown dwarfs.
And these are the ones Pew is specifically hunting. The literature always refers to brown dwarfs as failed stars.
Yes.
What does that actually mean? What is the physical mechanism of a star failing?
To understand the failure, you really have to look at how a star is born in the first place. A star begins as this massive collapsing cloud of hydrogen gas and dust.
Right. Gravity is just pulling everything together.
Exactly. As gravity pulls all that material inward, the pressure and the temperature at the very core begin to skyrocket. And if the collapsing cloud has enough mass, the core temperature reaches a critical threshold.
Which is what, like millions of degrees?
Around 10 million degrees Celsius. At that point, the kinetic energy of the hydrogen atoms is so ridiculously high that they actually overcome their natural electromagnetic repulsion.
They stop pushing each other away.
Right. They slam together and they fuse into helium. This is nuclear fusion. And it releases a staggering amount of energy.
Like billions of nuclear bombs going off constantly.
Pretty much. And the outward pressure from that continuous nuclear explosion perfectly balances the inward crush of gravity. When that balance is achieved, a true star ignites.
But a brown dwarf just doesn't have the gravitational muscle to reach that ignition point.
Precisely. That is the issue. A brown dwarf gathers a substantial amount of mass, far more than a gas giant like Jupiter, but it falls agonizingly short of the mass required to trigger sustained hydrogen fusion.
So it gets super hot, but it never quite catches fire.
Right. The core gets incredibly hot, and it might briefly fuse some deuterium, which is like a heavier isotope of hydrogen, but it can't maintain the main event.
So if it doesn't have that outward nuclear explosion, why doesn't gravity just crush it into a black hole or something?
What stops the collapse is actually this bizarre quantum mechanical phenomenon called electron degeneracy pressure.
Electron degeneracy pressure. That sounds intense.
It is. Basically, the electrons in the core physically refuse to be squeezed any tighter. It's a fundamental rule of quantum physics.
So it's just trapped in this weird middle ground.
Exactly. It's too massive to be a regular planet, but it completely lacks the nuclear engine to be a true star. It just sits there, glowing faintly from the residual heat of its own gravitational collapse.
Like a dying ember.
Yes, just slowly cooling off over billions of years.
And because they lack that internal engine pushing outward, brown dwarfs and even the smallest M-type red dwarfs are physically tiny compared to our sun.
Right. Oh, incredibly tiny. An ultracool dwarf is roughly 10% of the sun's diameter.
10%. So in terms of actual physical volume, how big is that?
They are barely larger than Jupiter.
Wow. Okay, so that brings the desk lamp analogy into sharp mathematical focus. Because the surface area of a star is proportional to the square of its radius, right?
That's right.
So if you shrink the star's diameter to 10% of the sun's, its surface area actually shrinks to just 1% of the sun's.
Exactly. You put an Earth-sized planet in front of that tiny surface area, and suddenly it's casting a massive shadow relative to the star's total output.
You've completely rewritten the geometry of the transit. You've skewed it to favor finding small, rocky worlds.
It's an elegant hack of astrophysical geometry, honestly. You maximize the planet-to-star size ratio. By creating that drastically higher contrast, you can use a relatively small, cost-effective instrument in space to detect signals.
It's signals that normally you'd need, what, a massive billion-dollar telescope to see?
Exactly. It lets you do incredible science on a budget.
Cost-effective is definitely the operative phrase there, because the PA team isn't starting from scratch on this hardware.
No, they have a huge head start.
Right. They are building on the legacy of these previous Canadian microsatellites, specifically one called MOST, which launched back in 2003, and NEOSat, which launched in 2013.
Right. And when people hear the word satellite, they usually picture, a school bus covered in gold foil.
Yeah, something massive floating around.
But microsatellites are a different breed entirely. They're essentially the size of a suitcase, or maybe a small washing machine.
A washing machine in space.
Basically. But the science they yield is entirely disproportionate to their physical footprint. Take MOST, for example. It stood for microvariability and oscillations of stars.
Which sounds very complicated. What was it actually trying to do?
Initially, it was designed for astroseismology.
Okay, so studying starquakes.
Exactly. Studying the acoustic waves bouncing around inside stars to determine their age and what they're made of. But it proved to be so incredibly precise that the team actually pivoted it to exoplanet research.
And it ended up making a huge discovery. Right?
Whoa, it delivered one of the most foundational discoveries in early exoplanet atmospheric science.
Okay, I want to get into this because this discovery involved a hot Jupiter exoplanet orbiting a star called HD 2109-458.
Kitschy name.
Super catchy. So MOST observed this system and discovered that this massive, blistering planet had a remarkably low albedo.
Right.
And albedo is just a measure of reflectivity. So like Earth has an albedo of about 0.3, meaning it reflects 30% of the sunlight that hits it.
Mostly because of our clouds and ice caps.
Right. But what MOST found was that this hot Jupiter was absorbing almost everything.
It was darker than fresh asphalt. It had an albedo nearing absolute zero.
That's just so weird to think about. A giant pitch black planet.
Right. Because prior to that observation, there was this working assumption that hot Jupiters might have highly reflective, bright cloud decks, maybe made of silicates or these exotic chemical compounds.
Like Venus, but way bigger and hotter?
Exactly. Venus is super bright. But most prove that the atmosphere of this specific hot Jupiter was absorbing the star's energy directly.
So what does a pitch-black atmosphere actually look like chemically?
It suggested a clear, totally cloudless upper atmosphere where alkali metals, things like sodium and potassium, were just absorbing all the visible light. Or perhaps it had incredibly dark, light-absorbing particulate hazes.
So it's basically covered in cosmic smog.
Pretty much. And that single finding forced atmospheric modelers to completely rethink how energy is deposited and circulated in these extreme environments.
All from a suitcase-sized satellite.
Exactly.
Then you had NEOSat follow up a decade later, tracking near-Earth asteroids and space debris. And both of these missions achieved world-class science, using telescopes that were only 15 centimeters in diameter.
Which is tiny.
It's literally a 6-inch mirror. You can buy larger telescopes at a hobby shop.
You really can.
So now, PUBD is bumping that up to a 20-centimeter telescope, which is, slightly bigger. But the real leap isn't just the size of the mirror, is it?
No, not at all. The real upgrade is the wavelengths of light it's engineered to actually see.
Right, because most of NEOSat worked in visible light.
Like our eyes do.
But POET is expanding into the near ultraviolet, visible near infrared, and short wavelength infrared.
And that shift into the infrared is absolutely non-negotiable given the targets they're going after.
Because they're looking at those ultracool dwarfs.
Right. If you look at an ultracool dwarf in visible light, you're essentially looking at a blank wall. They emit incredibly little visible radiation.
Why is that? Why are they so dim visually?
It comes down to Wien's displacement law. It's a fundamental principle of thermal radiation. Basically, it states that the wavelength at which an object emits the most light is inversely proportional to its temperature.
Okay, let's break that down.
Sure. So our sun burns at roughly 5,500 degrees Celsius.
Right.
Because of that specific temperature, its peak emission is right in the middle of the visible spectrum, yellow-green light.
Which is why our eyes evolved to see that specific light.
Exactly. But brown dwarfs and red dwarfs are vastly cooler. Their surface temperatures might only be 2,000 or maybe 3,000 degrees.
So they aren't burning nearly as hot.
Because they are cooler, the peak of their emission spectrum shifts heavily to the right. It moves entirely out of the visible spectrum and deep into the infrared.
Oh, I see.
So if you want to study these stars, and more importantly, if you want to capture enough photons from them to measure a 1% dip when a planet transits, you have to tune your instrument to the frequency they are actually broadcasting on.
You have to speak their language.
Right. You need sensors capable of detecting heat radiation, basically.
But doing that requires a highly specialized detector. You can't just put a standard CCD chip from a digital point-and-shoot camera into space and hope to see infrared.
No, the thermal noise would just blind the sensor.
And this brings up a really crucial question for me. A 20-centimeter telescope is still incredibly small.
Very small.
We have 10-meter telescopes sitting on mountains right here on Earth. Massive observatories.
Right.
Why bother sending an 8-inch mirror into orbit when we could just use a giant ground-based observatory to look for these infrared transits?
Because the Earth's atmosphere is an absolute nightmare for infrared astronomy.
A nightmare. How?
Well, first, you have the turbulence of the atmosphere itself, which causes the light from the star to waver and twinkle.
Right, the twinkling stars.
That twinkling introduces an unacceptable level of noise into the photometric data. It ruins the precision. But the really insurmountable barrier is water vapor.
Water vapor, like clouds.
Even just the invisible moisture in the air. The water molecules in Earth's atmosphere act like a solid brick wall for many bands of infrared light. They physically absorb the incoming infrared radiation before it ever reaches the ground.
Wow, so our atmosphere is effectively opaque to the very light POET needs to see.
Exactly the problem. You could build a 100-meter telescope on the ground, and it still wouldn't matter for certain infrared wavelengths, because the signal simply doesn't reach the mirror.
It's getting soaked up by the sky.
Right. So by placing a small, highly stabilized 20-centimeter telescope in the vacuum of space, far above all that water vapor and atmospheric turbulence,
it's just perfectly clear.
POET operates in pristine silence. It can gather uncorrupted photons with a precision that ground-based observatories can literally only dream of.
Okay, so that makes perfect sense. We have our perfect, highly tuned infrared camera in orbit, The next big hurdle is figuring out where exactly to point it.
Yes, target selection is everything.
Because you can't just sweep the sky blindly with a tiny satellite and hope a transit happens to occur while you're looking. Space is too big.
Way too big, and telescope time is expensive.
You need a highly curated list. Which brings us to the Peel Input Catalog.
The creation of this catalog is an exercise in ruthless optimization.
How so?
The initial sweep identified over 7,200 candidate ultracool dwarfs.
Okay, that's a lot of potential targets.
It is. But like you said, telescope time in space is a precious, finite resource. POET's primary mission timeline is just a year.
Oh, just 1 year.
1 year. So pointing the satellite at a star that has a low probability of yielding a clean transit is a total waste of multi-million-dollar hardware. They had to aggressively filter that list down to just over 3,000 candidates.
Okay, so how do they narrow it down? The first major filter was proximity, right?
Right. Proximity's huge.
They restricted the final catalog to candidates located within 100 parsecs from Earth. And just to bypass the astronomical jargon here, a parsec is about 3.26 light years.
Right.
So 100 parsecs is roughly 326 light years. In galactic terms, this is basically our front porch.
Oh, entirely. The Milky Way is 100,000 light years across. We are exclusively looking at our immediate neighbors.
So why restrict it so much? Why not look further?
It's dictated by the inverse square law of light. Even though POET is optimized for infrared, ultracool dwarfs are inherently dim. They just don't put out a lot of energy.
Right, they're embers.
And the intensity of light drops off exponentially as distance increases. If you select a target that's 1,000 light years away, the satellite simply won't collect enough photons to achieve the signal-to-noise ratio required to detect a transit.
It would just be too faint to measure a 1% drop.
Exactly. By staying within 100 parsecs, the team guarantees a high enough photon flux to make the measurements statistically viable.
Okay, so the distance filter makes perfect logical sense. But there's another parameter they use that feels completely counterintuitive to me.
The bright stars.
Yes. The catalog specifically excluded binary star systems, which I totally understand.
Right. Two stars orbiting a common center of mass, their overlapping light curves would make teasing out a planetary transit a mathematical nightmare.
It would be a mess. But they also explicitly excluded extra bright stars, which, if you are struggling to collect photons with a tiny 20-centimeter telescope, why on earth would you deliberately exclude the brightest targets in your category?
It really does seem backwards until you dive into how the detector actually works at a physical level.
Okay, explain the detector to me.
The sensors on a satellite are essentially grids of microscopic buckets called pixels, and they collect photons. Every time a photon hits a pixel, it generates an electron.
Right, basic digital photography.
Exactly. But if you point the telescope at a star that is too bright, those microscopic buckets fill up with electrons far too quickly.
They saturate. The bucket literally overflows.
Yes. The technical term is blooming. The electrons physically spill over into adjacent pixels, completely corrupting the image.
Oh, so it ruins the data for the surrounding area, too.
Completely ruins it. But even before you reach full saturation, there's another problem called Poisson noise.
Poisson noise, what is that?
It has to do with the fact that the arrival of photons from a star isn't perfectly steady. It's not a continuous, smooth stream. It follows a statistical distribution.
Okay, so it fluctuates.
Right. There's a natural, completely unavoidable variance in the number of photons hitting the detector from millisecond to millisecond. For an extra bright star, the sheer volume of photons means that the absolute value of this statistical noise is huge.
Ah. So the noise floor naturally rises with the brightness.
Yes, exactly. The tiny little dip caused by the planetary transit just gets swallowed whole by the massive, unavoidable statistical noise of that overwhelmingly bright star.
Wow. It's like trying to hear a pin drop inside a heavy metal concert.
Perfect analogy. It doesn't matter how good your microphone is, the background volume makes it impossible.
So you need stars that aren't too dim, but aren't too bright either.
Right. By focusing on a Goldilocks level of brightness, stars that provide enough photons to measure, but not so many that the detector saturates or the statistical noise spikes, POET maximizes its sensitivity.
That is brilliant. Okay, so they run the numbers on this highly refined Goldilocks catalog. And the computer models predict that POET can reliably detect Earth-sized exoplanets, specifically worlds between 1 and 2.5 Earth radii.
So true Earth-sized worlds and super-Earths.
But the models also highlight the orbital periods. They're specifically targeting planets with orbital periods ranging from 7 to 50 days.
And we really need to unpack the physical reality of a 7-day orbital period.
Because it sounds crazy. The orbital period is the length of a planet's year. Earth takes 365 days to complete a circuit around our sun.
Right.
If a planet is whipping around its host star in just 7 days, its orbital radius has to be incredibly small. It is practically skimming the surface of the star.
It's hugging it tight.
Right. If you put Earth on a 7-day orbit around our sun, it wouldn't even be a planet anymore. It would be a molten droplet of magma. The heat would strip the atmosphere away in a matter of hours.
It would be totally annihilated.
Exactly. So this seems to contradict the entire goal of the mission. We're looking for another Earth, presumably a place that could harbor life. Why prioritize planets parked in an absolute inferno?
Because around an ultracool dwarf, a 7-day orbit is not an inferno.
Because the star is so cold.
Exactly. It brings us directly into the concept of the habitable zone. The habitable zone, often called the Goldilocks zone, is the specific orbital band around a star where the surface temperature of a rocky planet is theoretically stable enough to maintain liquid water.
And liquid water is the absolute indispensable solvent for all known biology.
We haven't found a single living thing that doesn't need it.
So the boundaries of that Goldilocks zone are entirely dependent on the energy output of the host star.
The campfire analogy works best here, I think.
Oh, I like that. Let's hear it.
Our sun is a raging bonfire. If you want to not get burned, you have to stand quite a distance away. Earth sits comfortably in that outer band where it's just nice and warm.
Makes sense.
But an ultracool dwarf is just a tiny smoldering ember. If you want to feel the warmth, if you want your water to remain liquid and not freeze solid, you have to huddle intimately close to the fire.
So for a star that is 10% the mass of our sun and thousands of degrees cooler, the habitable zone just gets pulled in incredibly tight.
Very tight. So tight that a planet residing right in the middle of an ultracool dwarf's habitable zone will complete its entire orbit in a matter of days or a few weeks.
Okay, so the 7 to 50 day parameter isn't just a convenient byproduct of the transit method.
No, it is actively filtering for planets sitting right in the sweet spot for liquid water.
But wait, orbiting that close to a star, even a dim one, introduces a massive physical complication. At a 7-day orbit, the gravitational interaction between the star and the planet has to be immense.
You're bringing up the elephant in the room, tidal locking.
Yes, tidal locking. Because the planet is so close, the gravitational pull of the star exerts an extreme tidal force on the planet's mass.
Right, it's pulling on the rock itself. And over millions of years, this tidal friction physically slows the planet's rotation down. It slows down until its rotational period perfectly matches its orbital period.
Just like our moon. The moon is tidally locked to Earth, which is why we only ever see one side of it.
It's exactly the same mechanism. An Earth-sized planet in a 7-day orbit around a brown dwarf will have one hemisphere permanently facing the star, bathed in eternal daylight.
And the other hemisphere is permanently facing the deep freeze of space, locked in eternal night.
Right.
I mean, that sounds like a catastrophic environment for life. One side is a boiling desert, and the other side is a frozen wasteland of solid carbon dioxide.
Mm-hmm.
How does a planet like that support liquid water?
It's a great question, and it really comes down to atmospheric dynamics. Early models actually assumed what you just said, that tidally locked planets would boil off their atmospheres on the day side, which would then just freeze out and collapse onto the night side.
Leaving a completely barren rock.
Exactly. But advanced climate modeling over the last few years suggests a much more robust mechanism.
Really? How so?
If the planet has a sufficiently thick atmosphere, that extreme temperature difference actually drives massive planet-wide winds.
Oh, a global circulation system, redistributing the heat.
Yes. The incredibly hot air on the day side expands and rises rapidly, and then it rushes across the terminator line, which is the permanent twilight zone dividing day and night.
And it carries that heat to the dark hemisphere.
Right. This constant violent convection could stabilize the entire climate. It would prevent the oceans on the day side from boiling away and keep the atmosphere on the night side from freezing solid.
That is so wild. So life might actually thrive right in the middle, in that terminator zone.
Exactly. Perpetually bathed in the dim red light of a sun that literally never sets, anchored by these relentless global winds.
The environment would be profoundly alien, but physically, mathematically capable of supporting biology.
That's the current consensus, yeah.
And this really underscores the ultimate role of the POET mission, because POET is not going to definitively find alien life on its own right.
Oh no, a 20-centimeter microsatellite doesn't have the resolving power to image alien forests or, detect biological gases.
Right. POET-ILIT is essentially the ultimate cosmic scout.
A scout, yes.
Its mission is to survey the neighborhood, identify the handful of rocky planets residing in the habitable zones of these dim stars, and hand off their precise coordinates.
It acts as the vanguard for a monumental cosmic relay race. POET runs the grueling first leg. It stares at those 3,000 stars, watches all the static, and finally flags a confirmed target.
And then what?
Once POET determines the planet's exact size and the precise timing of its transit, it passes the baton to the heavy hitters of modern astronomy.
Of billion-dollar observatories.
Exactly. Observatories like the James Webb Space Telescope or the upcoming Habitable Worlds Observatory.
Because you can't just point a $10 billion machine like Webb at a random star and hope you get lucky.
Never. Telescope time is fiercely competed for by scientists globally. It requires guaranteed, high-priority targets.
Webb needs to know exactly when and where to look.
Down to the minute. And when Webb looks at a POET-discovered planet during a transit, it executes an incredible technique called transmission spectroscopy.
Okay, let's break down the mechanics of transmission spectroscopy, because this is basically how we sniff an alien atmosphere without ever leaving Earth, right?
That's exactly what it is. When the rocky body of the planet passes in front of the star, it blocks light, like we discussed. But a rocky planet isn't just a solid sphere. It has a thin halo of gas surrounding it, its atmosphere.
Right.
As the starlight streams toward Earth, a microscopic fraction of it actually grazes the very edge of the planet and passes directly through that atmosphere.
So the starlight is essentially being filtered through the alien air.
Beautifully said, yes. And different chemical molecules absorb different, very specific wavelengths of light. Water vapor absorbs one specific set of frequencies. Carbon dioxide absorbs another. Methane absorbs yet another.
It's a chemical fingerprint.
Exactly. So when Webb captures that filtered starlight, its spectrograph acts like a highly advanced prism. It breaks the light apart into its constituent colors. And the scientists, they just look for the gaps.
The missing wavelengths.
Right. If a specific frequency of infrared light is completely missing from the spectrum, you know exactly which molecule in the planet's atmosphere absorbed it.
Because it acts like a barcode.
A perfect chemical barcode. You have effectively analyzed the chemical composition of an atmosphere located hundreds of light years away.
And the ultimate prize in reading that barcode is finding biosignature gases.
That is the holy grail, yes.
We are looking for an atmosphere that is completely out of chemical equilibrium.
Right.
Because if you just leave a bunch of gases alone, geology and solar radiation will eventually cause them to react and settle into a stable, dead state.
Exactly. Look at Mars. Mars has an atmosphere in perfect equilibrium. It's mostly just carbon dioxide. It's totally geologically dead.
But Earth's atmosphere is wildly unstable.
Very unstable. We have high concentrations of oxygen, which is incredibly reactive. Oxygen really wants to bond with everything and pull itself out of the atmosphere.
But rusts iron, it burns wood, it doesn't want to just float there.
Right. And we also have methane, which reacts incredibly quickly with oxygen to form water and carbon dioxide. If you put methane and oxygen together, they naturally destroy each other rapidly.
So if a telescope detects both oxygen and methane in high concentrations on the same planet,
then something incredibly powerful has to be continuously pumping vast quantities of those gases into the air to replenish them. Otherwise, they would just neutralize each other.
Geological processes like volcanoes can produce some methane, right? And ultraviolet light breaking down water can produce a little bit of oxygen.
Sure, abiotic processes can produce trace amounts, but finding them in massive concurrent abundance, that is exceptionally difficult to explain via purely geological mechanisms.
So what's the most logical explanation?
The most logical explanation for a planetary atmosphere held perpetually out of chemical equilibrium like that is a global biosphere, life.
Plants exhaling oxygen and microbes producing massive amounts of methane.
Exactly, and this brings it all back to why the precision of PO is just so critical. Webb's ability to analyze an atmosphere is entirely dependent on the quality of the light passing through it.
Right.
By targeting ultracool dwarfs, the planet's atmosphere blocks a proportionally larger amount of the star's total light. The transmission spectrum is thicker, it's clearer, and it's so much easier for Webb to read.
It is such a beautifully synergistic approach.
Yeah.
Canada provides this agile, relatively inexpensive microsatellite to do all the heavy lifting of discovery. It filters out all the noise of the cosmos just to find the perfect geometric setups.
And then the massive international mega observatories step in to read the chemical barcodes. It really is an extraordinary testament to how collaborative and highly optimized the search for extraterrestrial life has become.
When you look at the entirety of this endeavor, it represents a really remarkable evolution in scientific thinking. We started by basically just staring at stars that looked like our own, using instruments that were only really capable of finding bloated gas giants.
We were looking for our twin with the wrong glasses on.
Right. We confirmed thousands of worlds that couldn't possibly support life, while the rocky, potentially habitable planets remain totally hidden in the glare. But instead of just hitting our heads against the wall, we changed the parameters.
The limitations of our tools forced a complete shift in perspective. If the sun-like stars are too bright, well, look at the dim ones.
Right.
If the habitable zone of a red dwarf is incredibly tight, use that to your advantage. Because those tight, fast orbits mean more transits and faster confirmation.
The physics that initially seemed like a massive barrier, the tiny size of the stars, the tidal locking of the planets, they are actively being weaponized to make detection possible.
It is the ultimate expression of scientific pragmatism.
The upcoming launch of Payat in 2029 isn't just about putting another mirror in space. It is about deploying a highly targeted strategy to sift through the cosmic noise of our local neighborhood, to ignore the bright, chaotic suns in favor of the quiet, red embers.
It'll map the orbital periods, measure the radii, and basically hand the absolute most promising 7-day-year super-Earths directly over to the heavy machinery to search for the breath of life.
The ingenuity of finding a way to measure a fractional dip in infrared starlight from a satellite the size of a washing machine, it just cannot be overstated.
It's amazing. It brings the loftiest, most philosophical question humanity has ever asked, are we alone, down to a literal matter of photon collection and noise reduction.
And as we wait for this mission to launch, it leaves us with a rather profound philosophical pivot to consider. When we look up at the sky, we instinctively view Earth as the standard, the baseline.
Of course we do. It's all we know.
Right. We have a massive, fiercely hot yellow sun. We have a nice, leisurely 365-day orbit. We have regular days and nights. And we just assume this is the ideal universal template for a thriving biosphere.
But the sheer math of the galaxy tells a very different story.
Because ultracool dwarfs, red dwarfs, and brown dwarfs make up the overwhelming majority of stars in the Milky Way.
Yellow dwarfs, like our sun, are actually in the tiny minority.
So imagine this scenario a decade from now. What if Webb points its massive mirrors at one of Poet's prime targets? What if it analyzes the atmosphere of a super-Earth tightly orbiting a dim red failed star?
A planet locked in eternal twilight with a year that lasts only 6 days.
Exactly. And what if it finds the undeniable chemical fingerprint of a robust, churning global biosphere?
It demands a total reevaluation of our place in the cosmic hierarchy.
It really would. It would mean our blazing sun and our long, varied seasons aren't the standard template at all. If life can take root and thrive in the fierce, tidally locked winds of a red dwarf system, it forces us to ask an incredibly humbling question.
What if we are the cosmic oddballs?
Exactly. What if the true, bustling metropolises of the universe aren't bathed in bright yellow light like our own, but are hidden away in the dim red glow of the galaxy's smallest inhabitants? The so-called failed stars might just turn out to be the most successful engines of life in the universe. And we are just the outlier, finally learning how to look in the dark.